Hello again and welcome to a new lecture. In this one we will discuss about pressure blocks and distributed loads. So let's start with the latter. What you see now on the screen are two examples of distributed loading conditions. On the one on the left, as you can see, the load intensity stays constant all along the beam from A to B and has a magnitude of 7 kilonewtons per meter. So we call this load a uniformly distributed load, or abbreviated a UDL. What we need to deal with is to determine the equivalent concentrated force that corresponds to this type of loading. So we need to establish its magnitude, and by definition this will be equal to the area under the load diagram. We need to establish its location, and this will be at the centroid of the load diagram, and we also need to establish its direction, which will be of course the same as the direction of the load intensity vectors. So in the case of the first load, the uniformly distributed load, we can calculate its magnitude, P, equal to 7 kilonewtons per meter times 4 meters, the length of the load, and that equals to a total of 28 kilonewtons. Its location will be at the centroid of the rectangle, so that's 2 meters away from the left end at A. And of course 2 meters from B. Now on the right hand side, you can see a load that varies linearly from a load intensity of 8 kilonewtons per meter at A to 0 at B. This is what is termed a linearly distributed load, or LDL, and its magnitude will be now equal to the area of the triangle that defines the load, 24 kilonewtons in total. The equivalent concentrated force will be located at 1/3 of the length of the triangle from its base, from A. So 2 meters from A and 4 meters from B. Now one thing you should note is that the load intensities are given in units of force per length. So that shows that the force is distributed in one direction, force distributed along a line in one direction only. So that's what makes this a distributed force. We can now imagine that a force can be distributed not only along a line, but also in the other direction. And that would be a force distributed across an area. To think about what could that be, maybe for example the pressure of the water in a big basin, in a tank at the bottom, or for example the pressure on the floor exerted by the students in a classroom. Is the classroom is full with students standing very close to each other, they're like exerting a force that's distributed across an area, somehow like the one that you can see in this diagram. So here you can see that the force is distributed both in the AB direction and in the AD direction, so across the ABCD area. Now we have to calculate again the equivalent concentrated force, and the principles are similar. The magnitude now will be equal to the volume instead of the area, but the volume of this entire, what is called pressure block. Its location will be at the centroid of this whole pressure block, and the direction will be of course the same as the pressure intensity. So in this case, vertically down, perpendicular to the area ABCD. So Knowing these principles, we can determine the magnitude of P as equal to 7 kilonewtons per meter squared times 5 meters and times 3 meters, the dimensions of the area. That amounts to a total of 105 kilonewtons. But in order to determine the location, this is a little more tricky because we are now in this three-dimensional space, and we know, however, to determine the centroid in 2 dimensions. So what we can do, we can divide these three-dimensional figures projected onto the 2 orthogonal direction. So if you look from above, like that green symbol is the eye looking towards the figure, you can see that rectangular shape with a base CD. So therefore, along CD, the force will be located midway between C and D, so 2.5 meters from D. And then we can do the same in the perpendicular direction, and we can see the other rectangular part of the load, so that the concentrated force will be located at 1.5 meters away from B. Now, if you look at the load intensity, you should know the units this time of force per length square or force per area. So now the force is distributed over an area. So that's what makes this distributed load over an area different from the distributed load along a line. The units are different, force distributed over an area. So in the international system of units, the unit for pressure, which is a force distributed by area, is the Pascal. So 1 Pascal equals 1 Newton per meter square. You should remember that because this is how you convert the units of pressure into newtons and meters. 1 Pascal equals 1 Newton per meter square. So what we've shown here is a uniform pressure block because the pressure intensity does not change across this area. So it has the same intensity, in this case 7 kilonewtons per meter square. Now, here's another example where the pressure intensity varies in one direction linearly. So in the CD direction or AB direction, it varies from C or B from 4 kilonewtons per meter square all the way down to 0. Now this is what we call the linearly variable pressure block. It's like a wedge, has the shape of a wedge. The principles that we apply here are the same as before, in the sense that the magnitude of the equivalent concentrated force will be equal to the volume of the pressure block, and that's 1/2 of the area of the triangle, side triangle, times the depth, 5.4 meters, so that amounts to 97.2 kilonewtons. And the location of the equivalent concentrated force is again at the centroid of the volume. Now if you project this in the 2 orthogonal direction, you can look from those directions and determine the location of the force into the 2 directions. So that would be 6 meters away from D and in the CD direction, and 2.7 meters away from B in the BC direction. Obviously, the load intensity of 4 kilonewtons per meter squared can also be expressed in the International System of Units as 4 kilopascals. So, thank you very much for watching this lecture on pressure blocks. We will discuss about stress blocks in the next lecture.